Introduction to Solutions in Aqueous Reactions, Double Replacement Reactions. In this tutorial, we will be looking at, well, obviously double replacement reactions, along with a worked example, an in-depth look at chemical equations, specifically what is a molecular equation versus a complete ionic equation, a net ionic equation, and spectator ions. And we're going to be linking all these together with some practice problems. Double replacement reactions, also known as double displacement, exchange, metathesis, or precipitation reactions, so take your pick. A double replacement reaction is a reaction that occurs when the cations, or positive ions, and anions, otherwise known as negative ions, of two soluble ionic reactant compounds are exchanged to form two new ionic compounds as products. One of the product compounds may be an insoluble precipitate, otherwise known as a solid. If an insoluble precipitate forms, the double replacement reaction is called a precipitation reaction. If no precipitate forms, no reaction occurs, as the reactant ions initially present in a solution are still present in solution after the two reactant chemical species are mixed. So a little review on the steps to complete and balance a double replacement reaction. Use the chemical formulas of the reactants to determine the ions that are present. Write the chemical formulas of the products by combining the cations from one reactant with the anion of the other, making sure to pay attention to the formation of the new products. And then finally, balance the equation at the end. And you might be saying to yourself, Dr. English, I have done this, I know how to do this, and yeah, I get it. But sometimes we make silly mistakes, and sometimes we just need a little review. So let's look at our two reactants, iron 3 sulfate and lithium hydroxide. So the first thing that I'm going to do here is I'm going to determine the ions that are present in these two chemical formulas. So iron 3 sulfate, well, iron is Fe. That Roman numeral tells me that this is Fe plus 3. Totally need that because Fe could be Fe plus 3 or Fe plus 2. And then sulfate is SO4 minus 2. Fantastic. Lithium hydroxide. Well, lithium can only be Li plus 1, and hydroxide is OH minus 1. So the first thing I'm going to do is write the correct formulas for my reactants. So my first one is going to be Fe subscripted 2, SO4 in parentheses with a subscripted 3 plus LiOH. So LiOH, and everything's good in the world. All right, then there's an arrow. The next thing I am going to do is say to myself, well, the Fe is now going to go with the OH, and the SO4 minus 2 is now going with the Li, and I know that I'm always going to put my positive ion first and my negative ion second. So we're going to have Fe plus 3, it's a plus 3, going with the OH minus 1. So when I cross these down, one of my products is going to be Fe in parentheses OH3 plus, and then I'm going to have Li plus 1 going with the, that's a plus 1, the SO4 minus 2, and I'm going to cross those two down. So then I'm going to have Li2SO4. Fantastic. Finally, I just need to balance the equation. Okay, in order to balance the equation, I need to think about where I'm going to start here. Like normal, I'm going to look at my parentheses. Let's start with the SO4. I have 3 SO4s right here, okay? So I need to get 3 SO4s on this side. So I'm going to put a coefficient of 3 in front of this whole thing. And so now I have 3 SO4s. Now, by putting that 3 in front of the Li2SO4, that now gives me a total of 6 lithium over on my product side. So I need to make it 6 over here. So I'm going to put a coefficient of 6 in the front, which now leads over to having 6 hydroxides right here. All right, 6 hydroxides. I already have a subscripted 3 outside of this bracket, which means I need to put a 2 right here. So that will make sure that my hydroxides are balanced. And then finally, I'm looking at my Fe. I have a 2 in front of my Fe. And oh, look, well, isn't that perfect? I have a subscripted 2 right here, so my Fe's are now balanced. So I've predicted my products, and now I have balanced my equation. So let's take this balanced equation and move on. We're now going to take a more in-depth look at chemical equations. So let's go over some definitions. A molecular equation is a chemical equation written to show the complete neutral chemical formulas for each compound in the reaction. So again, we're focusing on neutral chemical formulas. The equation is still referred to as a molecular equation, even though ionic compounds may be present, which is really, really weird. So we would call the equation that you see in this example as a molecular equation because they are all complete neutral chemical formulas, although every single one of these compounds does have ionic bonding involved. So don't get thrown off by that. Now let's talk about a complete ionic equation. A complete ionic equation is a chemical equation showing all of the species as they are actually present in solution. So here we have our balanced chemical equation, otherwise known as our molecular equation. And if we were to show this as all of the species as they're actually present in solution, knowing that Fe2SO4 is soluble, LiOH is a strong base, so that is soluble. Li2SO4 is soluble because of the presence of this group 1 metal, and FeOH3 is insoluble, okay? Insoluble. This would be my solid, so let's put a little solid down here. So if we were to represent this as a complete ionic equation, we would see something like this. So we'd see 2Fe plus 3, 3SO4 minus 2, 6Li plus 1, 6OH minus 1, 6Li plus 1, 3SO4 minus 2, and then finally 2FeOH3 solid. So what we're seeing here is that strong electrolytes, those ionic compounds that are soluble, strong acids, strong bases, are always shown as their component ions. In other words, they are going to be shown as ions. Weak electrolytes, such as weak acids and weak bases, are not shown as ions. Instead, they are going to remain in their molecular form. So we're going to come back to this a bunch of time. But note to self, weak electrolytes, weak acids, weak bases, which you have to know, are not going to be ionized. Spectator ions are ions that appear unchanged on both of the reactant and product side of a complete ionic equation. So if we had to go through here and identify our spectator ions, one would be 6Li plus 1 because it looks like this as a reactant. It looks like this as a product. Another one would be 3SO4 minus 2 because you can see it appears in the exact same way on both sides of the equation. Now we move on to the net ionic equation. This is an equation showing only the species that change. Only the species that change during the reaction. So if we take a look at our molecular equation, and then we have our ionic equation where we see everything as ions except for the thing that formed a solid, the net ionic equation would be 2Fe plus 3, 6OH minus 1, and 2FeOH3 solid. Now again, you don't need to put the solid in, but you better recognize that this thing is a solid. So it's only the ions on the reactant side that are formed in the solid. If every ion in a complete ionic equation is a spectator ion, then no reaction occurs. So to review, a procedure for writing net ionic equations. The first thing that you want to do is to write a balanced molecular equation for the reaction. That's what you would normally do in a double replacement reaction where you're just forming neutral compounds. Then you want to rewrite the equation to show the ions that form in solution when each soluble strong electrolyte dissociates into its component ions. So now we're looking at that molecular equation. We're identifying what's our strong electrolyte, strong acid, strong base. We're breaking them down into ions. Then you want to identify and cancel spectator ions with a single slash mark. So again, we're going to write our molecular equation. We're going to write our ionic equation, and then we're going to put a slash mark through, canceling the spectator ions on either side so we know what ions are involved in the reaction. So the 2Fe, the 6OH minus 1, forming our solid, and that is what we see in our net ionic equation. Let's do a little bit of practice. My first two reactants are Na2CrO4 plus AgNO3. The first thing I'm going to do is I'm going to look at each of these compounds and I'm going to identify what ions are present. So I know this is going to be Na plus 1 and CrO4 minus 2, and then Ag plus 1 and NO3 minus 1. Excellent. Then I'm going to go down to the molecular equation and I'm just going to recopy my first two reactants. So Na2CrO4 plus AgNO3, and then I'm going to put in my products. So that means my Na plus 1 is now going to go with my NO3 minus 1. Okay, so positive 1, negative 1. That just means this is going to be NaNO3 plus, and then my other two ions are Ag plus 1, CrO4 minus 2. I'm going to cross those down. No positive, no negatives, no ones. And my other product is Ag2CrO4. Fantastic. Now the next thing that I need to do is I need to balance this. So I can see right away I have two Ags right here. Two Ags. So I'm going to put a coefficient of 2 in front of this Ag. So 2 Ags. Now I have two NO3s, okay, which means I'm going to put a 2 here, 2 NO3s. Now I have 2 NAs. Hey, look, I already have 2 NAs over here. Good. I'm looking for my underlined parts to see what's left. 1 Cr right here, 1 Cr right here. Hey, this is balanced. Excellent. Now I'm going to move on to do my complete ionic equation. But before I do that, I'm going to go through and identify if everything's soluble or if I have a solid being formed. I'm going to go look at that. So Na2CrO4, well, that's soluble. AgNO3, that's soluble. NaNO3, is there anything more soluble? I don't think so. So soluble, but Ag2CrO4, yeah, that's insoluble. That is my insoluble product right there. So I'm going to keep that in mind. You do not need to circle that. I was doing that for a fact. All right, so complete ionic equation. All right, so I'm going to have 2 Na plus 1, because that means I have 2 moles of sodium ions. That's where this 2 right there is going right there. There's no parentheses around this CrO4, so I don't need a coefficient. It's an assumed 1. CrO4 minus 2 plus 2Ag plus 1 plus 2NO3 minus 1. Now you might be saying, Dr. English, why do you need the 2 in front of the NO3. This isn't parentheses. But don't forget about this 2 out in front of here. This 2 is distributive. So it means 2 moles of Ag, 2 moles of NO3 minus 1. Okay, awesome. Then I'm going to put my arrow in. NaNO3 is soluble. So again, 2Na plus 1 plus 2NO3 minus 1. I know my 2's are different. Don't hate me for that. Because again, this 2 is distributed. And then finally, I'm going to write my solid as just a compound to itself. It's not going to dissociate. So Ag2CrO4. So that just remains a solid. Put that little S in there for effect. Next thing I'm going to do is I'm going to cross out my spectator ions. You know I am. All right, 2Na plus 1, 2Na plus 1, 2NO3 minus 1, 2NO3 minus 1. Lovely. So what I have left here is CrO4 minus 2 and the 2Ag plus 1, which will come together to make my solid. So my final net ionic equation, where I'm trying to get to, and I usually like writing my positive ions first. It's just a thing. You don't have to do this. So 2Ag plus 1, it's a plus sign, plus CrO4 minus 2, arrow Ag2 CrO4. Excellent. And that should be good. So that is my net ionic equation. My spectators have been removed. Everything is balanced. I am accounting for everything. So that's example 1. For our next example, we have SrCl2 and Na3PO4. All right, let's see what type of magic we can make happen here. So we know Sr is going to have a charge of plus 2. Cl is going to have a charge of minus 1. Na is plus 1. And PO4 is minus 3. And you might be saying to yourself, God, that's so babyish. Why is she doing that? It's because, people, I make mistakes. And when I make mistakes, I get really angry at myself when I do the entire thing and I realize I made a mistake. So I do this to help me from making mistakes. All right, so I have my ions for everything, and now I'm going to copy down those reactants again. SrCl2 plus Na3PO4. And then I'm going to say to myself, okay, the Sr plus 2 is going with the PO4 minus 3, and the Na plus 1 is going to go with the Cl minus 1. So my first product is going to be Sr3 parentheses PO4 n parentheses 2 plus NaCl. Excellent. Okay, so now I'm going to double check to make sure that I did that all right, and it looks like I did. So now I'm going to go through and I'm going to balance my chemical equation. So I'm going to look for my parentheses. PO4, there's 2 of them right here. So I'm going to throw a 2, coefficient of 2, in front of this Na3PO4. So now my PO4s are balanced. 2 times 3 gives me 6 NAs. I need 6 NAs over here, which means I have 6 chlorines. So now I need 6 chlorines over here, which means I'm going to put a 3 in front of it as a coefficient. Chlorines are balanced. And then hopefully 3 SRs. Hey, look, 3 SRs. Goodness, I'm good. All right, so now I have my molecular equation and it is completely balanced. Let's move on to seeing what is soluble and insoluble in my equation. Well, my first 2 compounds have to be soluble, because if they're not, there's really no point of, combining them together. And then Sr3PO4, that's insoluble. According to my solubility rules, that's going to be insoluble. And then finally, NaCl, we better know that that is soluble. So my solid here, my insoluble product, is going to be Sr3PO4. So we'll keep that in mind as we're writing out our complete ionic equation. So now I'm going to take everything and I'm going to put it into ions. So 3Sr, so 3Sr plus 2. I need to take into account that 3 times 2 will give me a total of 6Cl minus 1 plus, same thing here, 2 times 3 gives me 6Na plus 1 plus 2PO4 minus 3. And then my insoluble product, my solid, I'm going to keep all together. So Sr3PO4 2 is my solid plus, and then 6Na plus 1 plus 6Cl minus 1. Okay, next thing I'm going to do is I'm going to go and look at my complete ionic equation, and I am going to look for spectator ions, ions that are the same on both sides of the equation. So 6Na plus 1, 6Na plus 1, 6Cl minus 1, 6Cl minus 1. So I am left with these two reactants and my one insoluble product. So the last thing that I need to do is recopy this net ionic equation, only showing the ions that are involved. So 3Sr plus 2 plus 2PO4 minus 3 will yield my insoluble product of Sr3PO4 2. Great. So there's another hardcore example. Let's do one more. Okay, here's our last example. We have HNO3 and Na2CO3. Well, let's look at HNO3. What do we know about HNO3? If you said, hey, Dr. English, that's a strong acid, you'd be right, which also means that it's a strong electrolyte. So this is going to ionize and form hydrogen ions and nitrate ions. And then we have Na2CO3, and we know that is going to be composed of Na plus 1, CO3 minus 2. So I'm going to recopy my two reactants, HNO3 plus Na2CO3, and then I'm going to say to myself, all right, well, the H plus 1 is now going to go with the CO3 minus 2, and the Na plus 1 is now going to go with the NO3 minus 1. So let's start with the Na plus 1 and the NO3 minus 1. When I do my chemical formula here, it's going to be NaNO3. Now, with my next one, this one's a little interesting because when I cross this down, I get H2CO3. Now, this molecule in water is very interesting, and this is a lead-in to a video that we're going to see in the future. So I'm going to kill the wonder a little bit here, and I'm going to say to you that H2CO3 is called carbonic acid when it's dissolved in water. And the crazy thing about carbonic acid is that most likely you are already very familiar with this, because this is what's found in any carbonated beverage that gives it that fun little snap associated with it when you're drinking it, because the carbon dioxide is actually pushing, trying to escape out of the liquid. So this molecule is very, very unstable. And when it gets into a situation where it is a product, it automatically breaks down into H2O plus CO2. Here's our molecular equation. So let's look at this one more time. We have HNO3, which is a strong acid, reacting with sodium carbonate, strong electrolyte, forming sodium nitrate, also a strong electrolyte. but as a result, we produced carbonic acid, H2CO3, which is pretty unstable and is going to break down into water and carbon dioxide. Water is a liquid and carbon dioxide is a gas, and in a double replacement reaction, a double replacement reaction will happen if you form a solid, a liquid like water, or a gas like CO2. So these are two factors that would definitely drive this reaction to completion. So now we need to balance this. I'm going to start with the NAs. So I have two NAs right here, two NAs right here. So I need to put a coefficient of 2 in front. Now, it is super tempting to just look at this as NO3 and to go over as NO3 over here, but I can't. And the reason why is that there is multiple locations for oxygens here, multiple locations for oxygens over on this side. So I just can't look at this and be like, oh, don't worry, I'll just keep it as NO3. That's not going to work. But I can say that I have two nitrogens. So I need two nitrogens over here, so I'm going to put a 2 in front. Two hydrogens. Hey, I have two hydrogens right here. And then I have one carbon. I have one carbon right here. And then I'm going to add up my total number of oxygens. So 2 times 3 gives me 6 oxygens right here. 3 oxygens right here for a total of 9 oxygens on my reactant side. 2 times 3, 6 oxygens right there, 1 oxygen right here, 2 oxygens right here, so 6 plus 1 plus 2, hey, that's also 9 oxygens. So, whew, thank goodness that is balanced. One more time, I'm going to go through and I'm going to identify what is soluble and can break down into ions and what needs to stay together. So HNO3, that's a strong acid. That's going to ionize into ions. Na2CO3, that's a strong electrolyte because of the presence of that sodium ion. NaNO3, that's a strong electrolyte because of the group 1 metal, plus all nitrates are soluble. But then we have water. Water is a liquid. That is going to stay together. That is not going to ionize. CO2, molecular compound, gas, not going to ionize. So these two are going to stay together. We are not going to touch them when we go on to write our complete ionic equation. Now for our complete ionic equation, we're going to write 2H plus 1 plus 2NO3 minus 1 plus 2Na plus 1 plus CO3 minus 2 arrow 2Na plus 1 plus 2NO3 minus 1 plus, hey, there's water. Don't do anything to it. Leave it alone. It is a liquid. Plus carbon dioxide. Again, don't touch it. It is a gas. It's a molecular compound. Don't touch it. So when we do this, we need to look for our spectator ions. What is the same on both sides? Well, if you said NO3 minus 1 is, you get a gold star. Or if you said Na is, hey, you get a gold star as well. So I've crossed out my spectator ions. So the last thing I am going to do once my spectator ions have been removed is to write my net ionic equation as 2H plus 1 plus CO3 minus 2 arrow H2O plus CO2. And now I have my net ionic equation for my last example. So what did you learn? We did a quick review of double replacement reactions with a worked example. We did an in-depth look at chemical equations, specifically focusing on the definition of molecular equations, complete ionic equations, net ionic equations, and how to identify spectator ions, and then we did a bunch of practice problems. Need more help? Feel free to contact me. Have a great day.